Welcome everybody to this seminar of the LIBREhub project. We are very fortunate to have the presence here of Edmund Humenberger, and he's going to give us a talk on open source FPGA tools for building research devices. Edmund is the CEO and co-founder of Symbiotic EDA, and so he has vast experience with these open source tools. And we're looking forward to looking at your presentation, Edmund. Please go ahead, and we can have minutes at the end for questions from the audience.
Okay, so I started pretty much 10 years ago to look into open source tools for FPGAs, because back then there was nothing. And the first FPGA we documented was the IS-40 from Lattice, and since then I continuously developed tools to make FPGAs usable with open source tools. So we are now in the stage where the open source tools can be used for serious projects. So here on the right, you see a board which is specifically designed for driving and for upgrading old E-beam microscopes, electron beam microscopes, which makes old hardware much more usable because it grabs the signal pretty early in the analog chain and digitizes it, and therefore the analog section of the microscope is not used, and this way the images can be of much higher resolution. So that's a way how to upgrade old equipment and make use of old equipment and cheap equipment. And the left side, there's also a research project where you can see how an FPGA is used for doing signal processing. So here you have, let's say, 8 analog inputs, 2 outputs, and different frequencies and different resolutions of the bit converters. So this is usually the analog front end, where you want to bring the signals into the digital domain, and then you use the FPGA to do the signal processing, to do the storage. For that, you usually also need memory. In this case, it's 2 GB of DDR3 RAM. And yeah, build some hardware, but the signal processing is done on the FPGA. This is another example where you want to use an FPGA for the signal processing. And why you want to use an FPGA in this kind of devices, we will see in the next slide. When you do image processing or you do signal processing, and you have very fast processes, or you have to have a very tight control loop where you want to record 1,000 frames per second, or you need a lot of sensors very tightly synchronized, let's say like with a certain particle accelerator. There is no way that you could use a software-based solution like a Raspberry Pi. When you need real-time processing, then you're asking for FPGA processing. Laser activation is an example where you want to do the processing of the sensor very fast and act back on the physical device. This is one of the examples of the open source physical instrument initiative, where you have some LED, you have some image processing, you have some optical elements, you have some physical elements. So this is all like how you build your science instrument, which is always a combination of mechanics, electronics, and physics. For example, you could add multiple polarized illumination systems. You could do multispectral illumination. You could do fast and sensitive sensing and to do active manipulation, like with lasers, like with the radio beams. And this is very much dependent on your physical or your biological element experiment. I also did look into Raman spectroscopy, where you have a stream of dots and you want to really sense when you have the dot, you aim a laser at the dot and you read out the data from your analog to digital converters very fast. And you also might able to act on what you have just sensed in real time so that you can do some sorting of your biomass. So the question is, why are science instruments expensive? And what I have seen is that obviously they are sold in very low volume, but they also have their development costs. So the development costs can only be shared between few sold devices when those devices are offered by a commercial company. And at the same time, when you go into FPGA-based solutions or software-based solutions, you often find that you have to license a lot of IP for interfacing different sensors, analog to digital converters, connect image sensors, doing storage. So that kind of development costs can accumulate pretty quickly. Because in the hardware domain, we still have the not invented here sickness. So obviously, there are custom built components like ASICs or mechanical devices. We cannot do anything about it. But as you have figured out yourself, open source can lower some of those costs by reusing designs, using open source designs, using open source tools, but also use hardware which was intended for a different use case, mainly that in high volume production, because they're very advanced components like laser diodes or sensing diodes or radar sensors are very advanced, but they're manufactured in high volume. So they are rather cheap. For example, we are using a Wi-Fi A to D converter, which can digitize 40 megahertz of spectrum in IQ, and the chip does only cost $4 because it's a chip which is manufactured for automotive. We have also seen laser diodes, which do cost several dollars. When you buy them as a scientific instrument, they might cost several $1,000s. The disadvantage of those misuse of devices obviously is it requires reverse engineering because usually documentation is not for that purpose. The researchers want to use the device, but for their original intended uses, like in automotive or in mobile communication, or like in fiber optic networking. One of the tools which makes it possible to build open source designs is obviously KiCad to do PCB designs, but also are there different RF simulators. And there is OpenXC7 as the open source FPGA toolchain for Xilinx. And now I will go a little bit to give you an overview of what have been developed in the last 10 years. So the first product we developed was Yosis. Yosis has a parser which can ingress hardware designs which are written in the language Verilog. And the result out from a synthesis step is a netlist, and that netlist of your circuit design goes into a place and route package, which then enables to generate the bit stream. And the bit stream is the configuration file which configures the FPGA to do whatever you want the FPGA to do. we can, for now, address with these tools, with NextPNR, with the Open FPGA Loader, different FPGAs from different vendors, like Lattice, which is so far the best supported. Then there's also the Chinese vendor Govin, and also the American vendor Xilinx, which now is AMD, but I still use the name Xilinx because AMD is kind of a broader name. There are other FPGA vendors which use our open source tools like Colon Chip and Renesas and QuickLogic, but they are not so relevant because they are not so widely used. When you write a hardware design in Verilog, you have to understand how Verilog designs have to be designed, have to be verified, have to be simulated, and it's a rather low-level language. And for this, there are other front ends to the OSIS where tools like BlueSpec or Chisel or Spinal HDL, those are different languages, but they generate as output a Verilog file, which then can be again used in the OSIS. The same is true for VHDL, which is a rather popular language in Europe, but not all of VHDL is supported in the current open source tools. That is true for BlueSpec and Chisel and Spinal HJs. And Silis is also a rather new language from French researchers, but it makes designers more productive once they learn the language. Since 8 years, there is also the tool called ICE Studio, which is a graphical design interface with the intention to teach 10 to 15-year-old children to program FPGAs. So you can put your elements like pins, like buttons into the user interface and wire them up, and then generate the bit stream and make the board do whatever you wanted it to do. It is also it also has the possibility to include a block where you write Verilog directly into it. So it's a rather flexible, but also an easy solution. What FPGA boards are there? I divided them into 3 categories. This one here is, I would say, the 100 mil category, where each pin can behave in any way. So you can make each pin a serial interface, an SPI interface. You can make it a parallel camera interface. It really depends on the design you do. You can also use pre-manufactured interface boards, like in the right lower corner. There we have an HDMI out PMOD module, which uses 16 digital I/O pins, or an A to D converter here, which uses 4 pins. And those boards can be put on a breadboard and connected up with wires, or the pins could be soldered on, could be put on an additional board. The limitation here is that the speed for each pin is usually limited to 100 megahertz or 100 megabits. So these kind of boards are not suitable for high speed. But the boards are available from very cheap, like the upper right corner for $20, to the more advanced in the middle, the Kintex boards. They go for $120, $150. Usually not above $200. The next category is the category of modules, where the FPGA does have a memory, usually a DDR3 memory, and that requires a large number of wires connected between the FPGA and the memories. And also for the power supply and for the boot up sequence. And those modules are available in different configurations from different vendors, and they are plugged into a baseboard. And those connectors also have the capability to transfer much higher speed. For example, on the right upper corner, you see a board which comes with 1 gigabit SerDes, and the lower end corner is a Kintex board which even has 10 gigabit interfaces. So the speed you can transfer to the FPGA and from the FPGA is much higher, which is sometimes important for high-speed digital signals, like the module in the right lower corner. And there are many boards which you can plug into an FPGA board to build your prototype research instrument, where you can choose what kind of analog digital converter you want to use, what kind of bits resolution you want to use, how many channels you want to use. And this makes it rather flexible to build this kind of projects. But it also makes it possible to build your own baseboard, so you don't have to really wire up the memories, take care of the power supply. So you can make your own baseboard and connect to those chips you need for your experiment. And then there's the third category, which is really custom boards. In the middle, the blue one is a software-defined radio board with an FPGA, with an USB interface, where you can program the FPGA to your need. Those are off-the-shelf boards for certain use cases, but those designers did build those boards for their specific use case. For example, in the upper left corner, this is a USB analysis tool, which is specifically designed to trace communication which is going on a USB line. Below that, in the lower left corner, is a board for radio astronomy. So there is the data communication link on 10 gigabit, which can be daisy chained, because a lot of those digitizer boards are needed for a radio telescope. And it also comes with a PTP synchronization hardware, so that every board is really synchronized to every other board at the nanosecond level. In the middle, lower side, we have a 10 gigabit Ethernet switch board, which we developed for the purpose of testing out new protocols, new routing protocols, new encryption protocols. And on the lower right corner, there is an general signal processing board, which can be bought off the shelf, but has specific use cases for RF measurements. Upper right corner, there is a sonar, which we design and use FPGA to do the signal processing for the multiple channel sonars. The open source tools we provide are also available in the cloud. So we run the CAS, symbioticeda.com server, where people can choose between certain boards in the template, like the RT35T. And there are several other FPGA boards from different families. And this is mainly to allow people to try out simple designs with their boards. We try to extend that in the future. what we also do is like we write open source IP so that it is much easier for people to build their own solutions using FPGAs. Might that be for internet connectivity over Ethernet, or might it be image sensors or memory controller? And we also in the process to operate a continuous integration platform where we can prove that all that IP is working for given boards. That's the open source toolchain for the Xilinx FPGA, which we continuously develop further. And I would invite everyone to look into the open source tools. And if you have any questions, please contact me. And now, please, there's time for questions.
Thank you, Edmund, for a very interesting talk. So, anybody has a question can raise a hand.
Me too. I also, maybe I can start with one of the questions. So Edmund, I thanks for your talk. That you mentioned several tools and many interesting examples. So in my question, maybe it's information you already said, but if you can explain in simple words again. So I'm just trying to understand what is open source in all this process and what is not, right? So the chips themselves are made by some manufacturer, right? So these are not necessarily, you're not going to make the chip in your lab or at home, right? And so is the open source part all the software that is required in the chain of production of all your FPGA implementation that is open source?
Well, there are two parts to the open source. The one is the tools to generate the configuration file for the FPGA. And the other is the design itself, like you want to make your FPGA a software-defined radio, you want to make your FPGA neural network accelerator, you want to make it a high-definition, fast-speed camera. So those are the designs. So what you do is like you take the design, which is written in a hardware description language like Verilog, and then you have to generate a bit stream out from that design. And the tool to do that is the synthesis tool, the place and route tool, and those tools are also open source. So these are the two components which are open source. The design of the chip itself is not open source.
And in the case of your company, for example, so you offer services that use all these open source processes to do the implementations?
Yes, so when we do a sonar system, as the example, we write the Ethernet controller, we write the UDP controller, we write the A2D interface, we write the bus system, we write the memory controller. And then we use all that design to synthesize a configuration file for the hardware we built. And that building of the bitstream is also done with our own tools. So when the tools are not good enough, we have to improve them.
Excellent, thanks.
My question, one of my questions, Edmund, is manufacturers are always like updating and upgrading their chips, and is the open source community for these tools, can the community keep up with upgrading and making the changes just to support all the new models?
Currently, we support the Series 7 of the Xilinx FPGAs. That chips are likely 10 to 15 years old, but they are used in a lot of designs still, and they're rather cheap. And also a big advantage of that chip is that they have been used in huge numbers in base stations all over the world, also in China. So for 3G and 4G. And those base stations now get replaced with the newer generation of 5G. And now those rather very expensive advanced FPGAs become available secondhand very cheaply. So we have currently no really incentive to go to more modern families. So the next generation from Xilinx was the UltraScale and UltraScale Plus family. We do not yet have support for those FPGA families. So we might work on the support for that family in the future. But so far, the open source community does not keep up with the new chips. There is the current most modern version of the FPGAs, which is called Versal. There is no support for that either. We think that it might be rather easy for us to upgrade to newer chips because chip vendors usually do not reinvent their chips from generation to generation. They improve them. And we have the tools to document those chips. And yeah, we have to update our tools, but we think it's not that hard. The most hardest thing is in the beginning to document the first family of chips. Like when we go into a new company like GoWinSemi, it's a totally new family, a totally new architecture, and the tools for that family need to be developed. So we did that for GoWinSemi, we did that for Lattice, and we did that for Xilinx. We do not yet have any support for a Phoenix and for Altera. And the reason is we have no need for other FPGA families. And if those companies want support for their chips in the open source tool chain, they are free to pay us for that.
Great, thank you. So we have a question in the chat there asking giving some ideas, some comments about using FPGA directly or using like off-the-shelf boards like the Raspberry Pi, for example. It's a question from Philippe Adrian.
Well, the Raspberry Pi is an ordinary SoC with a CPU, and you write software for it. It's easier to write Python, but it's very hard to get timing under control on a Raspberry Pi because it's a CPU and it's multi-cores, and so you never get timing right. So when you can build your solution with a Raspberry Pi and you're happy with the performance, then please do. So you only use an FPGA if you really need the high speed and the low latency, because with an FPGA you have a very tight control over the timing behavior. You use an off-the-shelf board to reduce the effort to build the solution. I showed several boards which can be made use of off the shelf. You do your own PCB if you don't find any other solution like we had with our Sonar system, because we have so many channels in parallel. When you want to digitize, let's say, 50 channels to the nanosecond, there is no way any computer can do that. So that's the reason why we build custom FPGA solutions.
Perfect. Vicente?
Yes, so as a follow-up to some of the topics you were mentioning before, so are the FPGA chip companies interested in contributing to the open source development of all these toolchain, I guess, of all these software tools, or they prefer to just offer their own software that only works with their chips?
That's different for every company. I think we are in an intermediate phase now, because 10 years ago, everyone hated the idea of open source FPGA tools because they said, well, you can get the tools from the FPGA vendors for free. So what's the point of having open source FPGAs? But The FPGA tools the vendor do provide, they are aimed at professional designers, because professional designers buy tens of thousands of chips for professional solutions. When you go at the university, those professional tools are much too complicated for a 1 semester, 2 semester course, because those are very powerful tools, and students are usually overwhelmed. So the first market for the open source tools was really the educational market, to keep it simple. And the first company we worked with was Lattice. So Lattice was like, well, yeah, what's the point of having open source tools? But due to the ease of use of the open source tools, a lot of communities, a lot of professors, and a lot of assistant professors use the open source tools in their teaching, because it's much faster, it's much easier to teach students circuit design, digital design with the open source tools, because the tools are also much faster and much easier to install. Like in Argentina, they did their own boards for the national education on electrical design work. This gave Lattice a lot of exposure at academic circuits. So for Lattice now, it makes sense to support us. So we have a very good commercial relationship with Lattice, because they get a lot of qualified and trained engineers out from the universities. So this adds value to their ecosystem of FPGAs for Lattice. With Xilinx, it's like there are pockets within the company which love what we do, and then there are the business people which say, well, how many FPGAs will I sell more in the next quarter if there is open source tools? And obviously, the open source tools do not move huge volumes of chips, but they allow researchers, like in the radio astronomy, to make use of the chips, which was originally not intended by the maker of the FPGA tools. So a lot of researchers are using the open source tools to beef up their PhD paper, because like when you use the official tools, you cannot add anything to those tools because they're proprietary. But with open source tools, you can tweak them, you can add an additional language. So a lot of language research is using the open source tools for the digital design. And it also provides a way to design digital circuits like chips, because the tools are pretty much the same. Either you address an FPGA or you address the manufacturing of a chip. So it's also for academics or for teachers, professors, a good way to teach students how to design a real chip, but deploy to the FPGA. And since 2 years or 3 years, we also have the possibility to let the designs really manufacture, as we now have open source design kits from Skywater, and it became much cheaper to manufacture a chip than it was 5 years ago. And obviously there are other companies which don't care, like Phoenix. I talked to them and they said, well, we don't see any point. I think maybe 10 years down the road, it doesn't make any sense anymore for the FPGA companies to run their own tools, as it doesn't make any sense for any chip vendor these days to run their own compiler. So there is the company Cologne Chip in Germany. They did design their own FPGA. And designing an FPGA is rather simple compared to writing the tool support. And as they are a small company, they said, well, we are not going to write our own tools, we just use the open source tools. The same thing goes for Renesas, and the same goes for QuickLogic. So there are 3 companies which are currently using the open source tool as their primary tool. And as the community grows and the open source design space grows, it will make less and less sense for the big vendors to maintain their own tools. But it will take them probably another 10 years.
Excellent.
Thank you.
Thank you very much.
Tobias,
I have a question.
Tobias, you have a question. Please go ahead.
Thanks, Pablo. Yeah, thanks, Edmund, for this, especially this last discourse, really insightful, I think, for me. And I would like to follow up a little bit more specifically around the use cases that we have. So we use the FPGA computers, and Pablo is just starting as well. They're not as cheap as some of the other boards that you mentioned, and I have seen some of the others, but I thought that they were too complicated for us to get started with. So the FPGA is useful because it's already, you can just run a web server. It's a full single board computer with the FPGA packaged on there. So it's kind of convenient to use. And the other thing is that there's already a community around it, and they have quite a lot of documentation. And above all, they have already some tools to interface this to Python. As you mentioned, Python is a good and easy language for lab scientists, especially bioscientists, also to develop. So we develop tools for the bioscience community, and for us, it's not only important that they're open source. So again, the FPGA is sort of an open source friendly environment, but it's not fully open source, the board itself, but that's fine for us in a way. But we try to develop things as open source as we can. So incorporating these workflows that you mentioned would be fantastic. At the moment, we use Vivado to compile our FPGA, which is not open source. But there's more things that are important to us than just that it's open source. So it also needs to be really easy to understand. So we would like, ideally, that a user, which is, let's say, a non-technology background biologist who is eager because they're doing their entire PhD on some equipment, let's say, and so they're quite keen, they have a little bit of time, and they should be able to understand key features of the design and tweak it, because we think that way we'll get to see really interesting laboratory equipment, because normally the users are not the same as the designers, and that mismatch generates a little bit of a gap in possibilities and usability and so on. And so we're really concerned with it being quite well documented and very easy to execute. Now, you mentioned that these open source workflows are easier, and in fact, this Vivado interface is very overwhelming. But could you give us a little bit more of an idea how this workflow goes, and how is it easier to use? Because I'm still a little bit confused by the number of different steps that you mentioned also that need to be done with the open source workflow.
Yeah, so I would use Ice Studio as an example how easy it could be. When you start Ice Studio, which is an application which runs, I think, on all operating systems, you just drag and drop your elements, like an adder or like an I/O pen or like a serial port. So you can drag and drop and wire up, which can be done by 10-year-old children. And then you push the button, and everything else runs in the background. Even the programming of the FPGA board is done in the background, and you only get a green LED or green button said everything is done. So this is the level of ease which can be done when the whole environment is set up. So Ice Studio supports about 20 different boards. So you just plug in the board into USB, and Ice Studio recognizes the board. So everything is very easy. But the thing is, very easy is hard. So someone needs to sit down and do the thing and design those user interfaces, the support for the different boards, those different elements like an FFT, and the ecosystem is driven by two things, by the wishes and the demand of the user, and by the capability and the funding of those who can build the thing. So it's like a little bit of a chicken egg problem. And I am doing this presentation here because I have the feeling that we now reach a point where ordinary users like biotech researchers might be able to use those open source FPGA tools, or at least contribute and tell us where to improve and try out. So there's always, let's say, more geeky ones and the more bio ones. So the geeky ones might figure out how to do things, might to go into discussion forums. And it's an ongoing process. So what I do here is I really push the envelope. I try to expand the user base. We try to be as helpful as possible. We do have funding to improve those tools, but we also need to have those users who tell us, hey, I want to interface that sensor. I want to interface that A to D converter. I want to do a Raman spectroscopy, because we have a lot of those components and we can build solutions easily. The perfect thing would be if you would say, hey, I got a research project for 3 years and we have a budget of $100,000 to build that science equipment. Can you build that? And we say, yeah, we can put these together. And I know the guy in Romania who would be able to build it and make it open source. So it's open source is usually not that well documented, and the reason is because it progresses very fast. So we are really in the fast progression phase, and we do not have really resources to keep up the documentation. We are currently making the high-speed interfaces work, like 10 gigabit interfaces, PCI Express, the really fast sensors. And yes, open source needs funding too. We get some funding from our side, but obviously research institutions like CERN do have funding too, which they can provide to improve the open source tools. As CERN, for example, did invest heavily in the development of KiCad for PCB design. And we hope to also have an economic environment where companies like our company can also make a living by providing development services and open source support and documentation to the user community. Does that answer your question?
Yes, I think pretty much. I mean, I guess it would be ideal also to see an example how it runs. I mean, the iStudio you say is more targeted towards high school students, so I guess that sounds to me like we should probably use the other pipeline you suggested.
Well,
but,
the Raspberry Pi,
it does.
The Raspberry Pi was also intended for students, for pupils. So it outgrew its original purpose. So when you address very low with a, for example, Raspberry Pi or Arduino, they were intended for children. So now engineers use Arduinos because they're easy to use. So and it's really our aim to make it easy to use. Our online platform is intended to make it easier to use, to improve the quality of the designs. We really want to expand the user base to make it less complicated, but it requires a lot of development effort to make things easy to use.
Thank you very much.
Okay, so thank you very much, Edmund, for a very interesting conversation, and thank you everybody for attending the seminar.